Welcome to Finite Element Methods. Today we'll be discussing the three-dimensional finite element analysis for structural mechanics. What are the finite element methods basic steps of interest? What we want to do is to establish the mathematical representation of the physical system. And that physical system is going to be governed by a partial differential equation. What we want to do is solve that partial differential equation over the domain of interest, which could be quite complicated. So the idea then is to determine a way of solving that. We start by discretizing the domain into smaller domains that are repeatable, they look like each other. And what we want to do then is to try to solve or approximate the solution over a single element. And by doing so, we can then assemble everything together, assemble the global stiffness matrix, and then apply the boundary conditions and solve the global system of equations for the unknown nodal quantities. But to get there, we have to formulate the weak form. And the reason we want to formulate the weak form is to enable the use of the weak form Galerkin. And the idea is to take the strong form, derive a residual error, make it orthogonal to weight functions, and what that helps us to do is that when we integrate by parts, we can reduce the continuity requirements, which means I can use a lower order polynomial, and then I only have to satisfy the essential boundary conditions. So that will take us to the endpoint really, really quickly, and it will allow us to get to the bottom line, which is to find an approximate solution to a very complicated aircraft or a radiator. Whatever it is that's complicated, the idea is to approximate the solution over that domain. And we can only do that if we could break up the domain into simple elements. If it was a one-dimensional problem, such as lines, rods, beam, trusses, or frames, then you will select an element like that. Depends what the structure looks like, you will then make a representation and you will idealize that structure accordingly. A two-dimensional element, for example, will be a triangle or quadrilateral. These elements are very simple elements that can be used to discretize the domain. We then have the three-dimensional elements, which is the subject of what we plan to discuss right now, and it tends to be the more computationally intensive and expensive. Here you see a tetrahedron, and here you see a hexahedral, or a brick element here. These elements can be used to discretize a three-dimensional domain for which you cannot use the simplifying assumptions of the one-dimensional theory or two-dimensional theories. If you cannot fit the criteria for modeling in this way, then you have to go to a three-dimensional type element, which is computationally expensive. Here, what I'm showing you is the different comparisons of a one-dimensional element. Just these are just beams, and that makes sense because these are frames, and so these frames can help react to loads in a very, very effective manner. But using three-dimensional elements for these beams will be very ineffective. There's no point in doing that. When I go to the two-dimensional triangular elements, this is what you will see here as an example. This makes sense for structures that are fairly thin or very, very thick, but I can represent them as two-dimensional because that's sufficient to model the system. Then you have the three-dimensional brick elements, which are more complex in nature, and they're capable of simulating very complex behaviors. And you cannot really use two-dimensional or one-dimensional, so therefore you're stuck in doing three-dimensional brick elements. Here you can see several models being used to represent a 3D geometry. So here you see a 3D domain discretized using hexahedral elements and tetrahedral elements, linear or quadratic. And by doing so, you can then represent the stress states within the system. Using a two-dimensional model could be okay. For example, here I could have used two-dimensional element, a shell element, and I will show and discuss shell elements later. But a shell element could be sufficient because of uniform thickness, and it's possible to be able to get there. But if this is very short compared to a thickness, then you start to want to use the three-dimensional elements. They're more effective. Here you can see an impeller model. You can see here is an engine component. You can see here the three-dimensional aspects of it. And so here a 3D model was used and is very effective at that. And you can see here that they try to use hexahedrons alone to get to that mesh. A more complicated part, such as this one, which is an engine part, you can see that this component requires tetrahedron elements because of the complexity of this system. However, using quadratic elements, second order tetrahedral elements could be a good choice because of the high curvatures, and you may have high stresses that need to be considered. I want to remind you the 3D elasticity finite element formulation. The diagonal terms here are called the normal stresses. The off diagonal terms are called the shear stresses. The normal stresses, and I already discussed this before, but I'm kind of basically providing a summary right now. So we already covered a lot of these aspects. Here you can see Taiwan 1, which is the stress, and tau to 2, which is a stress that's axial and perpendicular to the two phase. Tau 1 is perpendicular to the one phase. Tau 3 is perpendicular to the three phase, and they're acting together to stretch that cube. The off diagonal terms are acting to shear the cube, and the strain components that we had discussed are epsilon xx, epsilon yy, and epsilon zz, and I didn't show epsilon xx, but all these three strain components here also act to stretch the cube, while the shear components act to shear the cube. The change in angle is represented by gamma xy, gamma yz, gamma xz. Sorry, epsilon x was actually here, and I apologize for that. But here, u, v, and w are the variables of interest. X, y, and z are the coordinates of this cube. Here I'm using x1, x2, and x3, but in essence, this is x, y, and z. U, v, and w are the deflections corresponding to the x1, x2, and x3 directions, and those are the ones we're after. Because if I can find the deflections u, v, and w, I can determine the strains, and if I know the strains, I can calculate the stresses using the constitutive law. So from there, we want to then look at what we already discussed, which is the stress equilibrium equations. And the stress equilibrium equations that we derived are these three equilibrium equations of elasticity. And this considers the body forces B with components Bx, By, and Bz, the density, which is we're going to assume is uniform. Ax, Ay, and Az are the acceleration vector, and the stress components are part of this equation. And there's again 9 stress components, but 6 of them are independent because the off diagonal terms are equal to each other, while the diagonal term is tau 1 1, tau 2 2, tau 2 3 3, and there's 3 of them there. So again, 6 unknowns, 3 equations because the body forces, density, and accelerations are known. And these were derived using second Newton's law, integral form, and it was discussed much earlier um, in time. We also discussed that I need to determine the relationship of stress to strain. So strain equals this constitutive law for orthotropic materials times the stress vector. And due to symmetry, the off diagonal terms are equal to each other. That's the basic idea here. That you need to measure these properties have to be measured, and they're measured doing constituent, basically testing. For example, the uniaxial test can provide EXX. You can do a uniaxial test that provides your EYY, and the Poisson ratios can be measured by installing strain gauges and measuring the contraction in the direction opposite from where you're applying the load. So if I'm applying a load in the X direction, I want to then measure the contraction in the Y and Z directions because that's going to allow me to determine the Poisson ratios. Shear tests can also be performed, and altogether you can fully characterize these constitutive metrics. And from there, once you have this expression of how stress relates to strain, and given that I know how the equilibrium equations are expressed in terms of stress, And given that I know the strain field in terms of deflections, I have sufficient number of equations and unknown. I have 15 equations and 15 unknowns. There's 6 equations here. I have 3 equations here, that's 9. And I have 6 equations here, that's 15. And then when I look at the strains, I have six stress components, 6 strain components, and then I have basically 3 deflections are unknown. And there's a total of 15 and 15 that need to be solved. You can also invert the relationship. So that's written in terms of stress equals this times the strain. That makes total sense because that can by inverting this equation here. And the isotropic version of that looks a lot simpler. Isotropic means that there's no directional dependence. It's simply an isotropic relationship where the modulus and the Poisson ratio are the only things that matter because the material behaves the same in every direction. So from there, what I have here then, in summary, these are the questions we really have. We have the 3 equilibrium equations, which I can write in a smart way. And I already covered this, but I'll cover it again. So I can put this constitutive equation, these 3 equilibrium equations, I apologize. These 3 equilibrium equations can be put in this format with a vector now that has a stress components. And there's 6 stress components, and what I want to do is show you quickly that I get the first equation by multiplying the first row by that column. And the derivative respect to x of that first one is that term. And then 0 times that, nothing shows up. 0 times that, nothing there. 0 times that, nothing there. And then you have these last two that get multiplied by these last two stress components. You can see exactly that those are the 2 components we're talking about. So you can see that this arrangement of this matrix is actually quite convenient because I'm able to write these 3 equations in matrix format, which is extremely convenient in finite elements. The second equation, the same, very similar way, you can see how this gets multiplied by sigma yy, and that's that term right here. Derivative with respect to x is times the last one is that very first term there. You can see that it turns out very nicely. That second line, second row times that stress vector multiply gives you that second equation. That third equation the same way, I can take that row times that stress vector and get that third equation. I'll call this L bold. L bold here is is a differential operator, and it's convenient to write in that manner. I'll put a transpose there on purpose to show you that if I remove the transpose, I can use that later. The stress vector bold will be put in there, and the body forces will be put in B bold. I here on purpose made the acceleration term 0, but I could have kept it. It's not very difficult. And in my book, actually, I keep it and show you how to deal with it. When I look at the 6 strain deflection relationships we showed here earlier, these are the 6 strain deflection relationships. I can write that here in this matrix. So that first row times that first column gives you the first term. Second row times that first column gives you that second term. And you can see that multiplying these rows times these columns, I'm able to get the relationships I showed in the previous page. If you look, let's look at shear. Twice epsilon yz, which is gamma yz, is really the fourth row. So 1, 2, 3, 4. So this times v plus this times w. And you'll see that that operation gives you exactly what epsilon yz is. And that's what we see here is partial v respect to z plus partial w respect to y, which is just changing angle of initially 90-degree angle between two lines. And you can see it's working out. These operating on that, this operating on that gives me that. You can see that all this works out. Now, what I want you to notice is that when I compared it, and this is the exciting part about how this worked out, is if you look at this 6 by 3 matrix operator, that's the same as this one, but it's the transpose of this one. So you can see that that first row is that first column. The second row is a second column, and so forth. You can see every single one of those is shown here but that's a transpose. So if I take L bold transpose and make it the transpose of that, I get L bold. In essence, L bold is this, and the transpose of L bold is that. This is the deflections are unknown, so U bold, and this is the strain vector epsilon bold. So L bold times U bold equals strain bold. Great. Now I have a relationship of strain in terms of deflections in a very compact manner. And I also have the three equilibrium equations in a very compact manner. You can see here the stress strain relationship. I can put that also in a compact manner. This is stress vector sigma bold. This is strain vector strain bold, epsilon bold. And I will just focus on the isotropic version of this theory. So now that we have established the 15 equations and 15 unknowns, now is the time to go ahead and figure out a way of solving them. So we have three governing equations that can be written in a compact form in this manner. So let's see what's going on here. So I'm going to include the acceleration term. These are the three elasticity equations. And really what we're trying to do is apply a load to the body, an aircraft, and determine the stresses in the body and then determine when the structure could break. We want to design the system so it doesn't break. Here you can see we have L bold transpose sigma bold plus B bold equals rho U bold double dot. And here you have your three equations. Now we know that stress equals C bold times epsilon bold. Epsilon bold is L bold times U bold. And you can see here that the strain is L bold times U bold. And so now we can plug all this into this equation. So we get that plus B bold equals rho U bold double dot. And so now what you see here is that we have a single equation that only depends on deflection. So we've simplified the problem. And really, we're after deflections. That's really what we're after. And what you have here is really three equations. This is a 3 by 6. You can see that here. 3 by 6. C bold is 6 by 6. L bold is 6 by 3. You can see that here. 1, 2, 3, 4, 5, 6. And so all this gives you a 3 by 3. 3 by 3 times 3 by 1. So that's basically three equations right here. Remember that L bold is all this. And we're specifying boundary conditions on this boundary here. Energy methods for a general element. So what are we looking at here? The energy methods for a general element formulation. How we get there? So we have the total potential energy of the system under applied loads. Pi is a function of U, V, and W. And this is your strain energy of that system minus the body forces, minus the traction, the body forces, the potential energy due to body forces, minus the potential energy due to traction forces applied. Basically, you have traction forces applied on the surface, and that's what this integral is over the surface, while body forces are acting on the volume of the material. And then you subtract any point loads that are applied, and these are the potential energies due to those point loads. So yeah, here's your strain energy, total strain energy, and then here you have the potential energy due to loads applied. Body forces integrated over the volume, traction forces integrated over the surface, and then you have the point loads applied in the system. That is your total potential energy, and the idea is to find U, V, and W that minimize pi, because the ones that minimize pi are the ones that render the system in equilibrium. In compact form, we can write this very simply as sigma bold transpose times epsilon bold. Here, what you see, we have a scalar quantity by doing this calculation. Um, that can be easily written in this format, minus B bold times U bold. And here what you have is body forces times the deflections U bold. Very simple incorporation of that here. These are volume integrals, so that's easy. And then you have the here you have the traction bold times u bold, very simple as well. And this potential energy is also q bold times u bold. If we put px, py, and pz in a vector, we can quickly multiply this by that. I'm considering t bold to be a column vector. Q bold is also a column vector. That makes it easy to do this multiplication. So I could then apply the Rayleigh Ritz because Rayleigh Ritz works really well when you have a functional. That's the one you see here. And again, in my book, I go and derive it using the weak form Galerkin as well. But here we're going to use the total potential energy approach with the Rayleigh Ritz. So if I choose an approximation function for the displacement field that looks like this, U, V, and W are the deflections in the X, Y, and Z directions, or X1, X2, X3 directions. And this is a node 1. And these deflections are at node 2. These deflections node 3. And these deflections are node M. So we're going to say, keep it general. So there's M nodes, but in this element, right? That way we can apply this theory to anything we want. So M nodes for this element, which is three-dimensional. What you see here is I can now express U, V, and W in terms, these are the deflections within the element, and we can write it so it's a function of the nodal quantities. So what is that? We can use the shape functions to accomplish that. Note how I'm going to apply the shape functions in such a manner that the first equation here is U at and at any point within the volume, which is X, Y, and Z. And I'll multiply N1 times U1 plus N2 times U2 plus N3 times U3. That's why you have zeros there. So you're just multiplying against U1, U2, and U3, and so forth. For V, I'm going to start it here in the second location because I want N1 to only multiply V1, N2 to multiply V2, N3 to multiply V3, and so forth. That's really what I want, and that's why you see that there. In the third equation, you see that N1 is multiplying W1, N2 is multiplying W2 until Nm, which multiplies Wm. So these deflections, which are within the volume, are equated in such a way that these are the matrix of shape functions times the column vector of nodal unknowns. So that's the approximation function. Recall, Rayleigh Ritz requires an approximation function, and this is my approximation function for each of these unknown quantities. Because again, there's three unknowns here, U, V, and W. And the reason there's three unknowns is because I was able to write the functional, so it's only a function of U, V, and W. And I have to find U, V, and W that minimizes pi. But I'm going to use the nodal coefficients to be the nodal unknowns. The unknown coefficients, I'm selecting them to be the nodal unknowns. And the shape functions are selected in a smart way so they satisfy the partition unity property and the Kronecker delta property. So with that said, this whole thing is in bold. This cube bold is this whole thing. And I'm ready now to substitute this into the potential energy. Looking at a single element, the total potential energy is this whole thing minus this minus that. You can see that what I've done here is plugged in. So I know what sigma bold is and epsilon bold is in terms of these quantities. So let's look at what sigma bold is. Sigma bold is C bold, L bold, U bold. L bold is a matrix, the operator matrix. And so I'm going to plug that in. And notice how epsilon bold is just L bold times U bold. So I have CLU bold for stress. And for strain, I have L bold, U bold. So that came from here. Sigma is sigma here, bold is CL, C bold, L bold, U bold. And strain is C bold, sorry, L bold, U bold. And that's what you see here. And again, I encourage you to write everything out to make sure you're following it. Um, and then the rest is easier. I basically have this expression, and this expression. U bold is known, is this is U bold. and that's equal to m bolt times q bolts. When I can plug that in here now, in where I see u bolt, I just plug it in, as you see. And I can then apply this transpose operator on the whole thing. And what I get is Q bolt transpose gets factored out here. L bolt, M bolt is this one. C bolt transpose is the same as C bolt because symmetric. L bolt, M bolt is this. And Q bolt is this. So now I'm ready now to go ahead and um, basically it is convenient to define B bolt to be L bolt times M bolt. So all that is taking these shape functions and applying that differential operator to these shape functions. So yeah, you can do this calculation separately and plug it in back here. Now notice how the Q bolt is the only unknown now. So let's look at what B bolt is. So I have B bolt to be L bolt times M bolt. L bolt is a matrix operator, the differential operator. So I'm going to apply that on this shape function matrix. So you can see easily that this just this multiplied by that. So that gives you the partial respect to x of n1 and so forth. So this is a very easy multiplication that gives you B bold. This is also the so-called strain deflection matrix. And the reason is because a strain equals B bold times Q bold. It gives you a transfer function between the nodal quantities and the strains within the element. So that's the benefit there of this B bold equation. We can substitute this into the total potential energy, which then gives you the following equation. So let's plug that in. I'm going to plug this B bold, L bold, M bold. Anywhere I see L bold times M bold, I'll plug that in. And that just simplifies to this. So then I'll go ahead and minimize. The idea now is to minimize. But by the way, I can take Q bold transpose, puts outside of the integral, and I can do that because these quantities that you see right here do not depend on this integral. They're just nodal quantities. But the next step is to minimize pi respect to Q bold and set that equal to 0. And that's simply this right here. No problem. This goes away. So I have this, and this is this, and that's that. So very easily, just remove the Q bold and then 1/2 Q bold as I've done before. I showed you already that this is how you minimize pi respect to Q bold, and we proved it very early on. So this is what I get now, and these are all easy integrals to calculate. The only thing that's not known is Q bold, and that's for this single element. We can easily add the kinetic energy. I dropped that term, but I can add it, and it's just the integral rho m bold transpose m bold dv q bold double dot. In my book, I actually discuss how to get this term from the very beginning, but for the purpose of this discussion, I think it's just fine to go through this. These three terms can move to the right hand side, so it just simplifies everything. The q bolts are on the left hand side, and we can just now apply the finite difference method so we can then time march the solution. I can now use the isoparametric formulation, and if I were to use a hexahedral element, which is a cube element, it has 8 nodes, and I can convert this integral, this volume integral, into a triple integral that goes -1 to 1, because a cube can be put uh, in a coordinate system where the center of the cube is at 0, 0, 0, 0, 0, 0, and the limits of that cube go from -1 to 1. So it's a cube hexahedral in a natural coordinate system. Uh, I can take any hexahedral element of any shape and map it into a subparametric element. So what does that mean? I can take every single element here that looks of different shape and map that into a single hexahedral element that's cube, is a cube element. And the benefit there is that now the shape functions are the same for every element, and the derivatives of the shape functions are the same for every element. The dv quantity becomes the determinant of j, and dv becomes deep c d eta deep zeta. And so again, that's true for every single of these quantities. This is a volume quantity as well. And this is a surface quantity, and that's a little bit harder to deal with, but it will be following the procedures we discussed in the very previous lecture on how to deal with surface loads. The Jacobian here is given as that. And notice how the Jacobian needs to be calculated. We need to find uh, basically the mapping between the true coordinate system that I'm dealing with and the natural coordinate system. And you can accomplish that by using shape functions. And I'll discuss that. But we need to calculate Jacobian to plug it in here so that we can have everything in terms of the natural coordinate system so that all the shape functions are the same, all the integrals for every element are the same. And in addition to that, we can then accomplish um, the derivatives also are the same for every element. So that's the basic convenience of isoparametric formulation. So what I'm going to do to turn that hexahedral to a cube, which has 8 nodes, or it could be m nodes. We can keep it general. So I have the coordinates of every node. Node number 1 has coordinates x, y, and z. Node number 2 has coordinates x2, y2, z2, and so forth up to the mth node, xm, ym, and zm. So x, y, and z here depend on psi, eta, and zeta. So these are, we're trying to find a way of relating the coordinates x, y, and z in the global system, and this helps in related to the natural system. So I plug in the natural coordinates, -1, 1, whatever I want within that cube, and it returns for me the coordinates in the global system. So it's a mapping, right? And the idea here is to use the same shape functions I used to approximate the deflections. Use the same deflection approximations. Use the same thing to then do that mapping that I want. And so C bold here is the vector of coordinates that I know because I know the coordinates of that cube. I know what they are. And that's fairly simple to deal with. Um, I know those values. I know the shape functions for every element because they're gonna be the same in the natural coordinate system, and I'll discuss what they look like for a cube. But generally speaking, that's the process, and I know how to do that in a very simple way. So yeah, so these x, y, and z becomes equal to n bold times c bold, where that's the vector of nodal coordinates, and I know those values. These are just numbers. With this information, I can then calculate the Jacobian very easy. I can find the derivative of x respect to c very easily. All this can be calculated because c bold is all numbers and the shape functions are the same for every element. So I should be able to calculate these derivatives. I did it here. Um, I didn't do it here, but you understand how to get there. Um, I also want to show you that I need to calculate b bold. B bold, that b bold needs to be calculated. I need to find this derivative. Basically, b bold, we need to find this partial respect to n1, partial respect to n2, and so forth. I need to do that. But now n1, n2, and n3 up to nm are in the natural coordinate system. So finding this partial respect to x, y, and z is a little bit of a problem. Now, I discussed how to do that before. We can use the idea of the Jacobian. Notice how the Jacobian connects these derivatives, which I can actually do calculate. I can do that calculation. And that allows me to find basically what are the, I can find these derivatives that way, right? Those are the ones I want to find. And for a hexahedral element, there's 8 shift functions. For a tetrahedron, you have 4 shift functions. And I'll show you what they look like. What I really want to find is these derivatives. Why? Because I need them. You can see here, B bold, I had to find the partial of n1 with respect to x and so forth, but n1, n2, n3, and 4, and so forth are in the Unfortunately, they are in the psi, eta, and zeta coordinate system. So, but I know this quantity, I know this whole quantity, so we can invert that and get the derivatives that I need. This was discussed in the previous lecture, and we also covered for the 1D isoparametric formulation, but I'm just going over that again so you can see how to formulate it for 3D. Once I get to this point, I'm ready to find these derivatives. I can do that very easily. And notice how when I do this operation, let me remind you, if I do this operation in blocks, so just multiply this in blocks, um, it makes it easy because these are 6 by 3, so I can apply it in blocks. You can see I did that here. I plotted in blocks, so B1, B2, B3, B4 up to BM, and BI is just this right here. So think of this plugged in here for B1, B2, B3, B4. The only thing changing is the NIs. So you can check it yourself. It works really nicely. Uh, but these derivatives are required. I need to find them. So we need to figure out a way of doing that. And so these allows us to get there. J inverse times that allows me, and I know all these numbers, all these calculations. I know J for every element, the Jacobian. So I should be able to calculate this and calculate B bold for every single node because I have 8 shift functions for a hexahedral and 4 shift functions for a tetrahedral element. Once I do that, I'm ready to plug it back in here. And now I have everything in the isoparametric formulation. So let me jump straight to the 3D element types. So you have the tetrahedral element, the second order tetrahedral element. And I'm not going through every single detail at this point because we already practiced sufficiently on the heat transfer problem. And the procedure is basically the same over and over. And it's just not that different. These are tetrahedrons, a second order tetrahedron element, first order hexahedral element, and that's a second order uh, hexahedron element. Now, these are 20 noded elements. That's 8 nodes. This is less. This is 10 nodes. And then this is 4 nodes. Let's look at the shape functions for a 8 noded element. And so the shape functions for 8 noded elements are given by this right here. Now you may ask me how you use this. Well, the first shape function is n1. So you go here to this table of number one, n1, and these are the numbers you're going to plug in for psi, eta I, and zeta I. By plugging these numbers in, you get your first shape function. And then you look at the second shape function as well. So n2, and then I can plug in each of these values into this here, and so forth. I can then get my 8 um, uh, the 8 shift functions. I apologize. So this is how you will do that. 8 shift functions, you can check it yourself that meets the partition unity that also satisfy the Kronecker or delta properties. The C3D20 element is more complicated but not too difficult. It has these middle nodes there. The way you derive the shape functions is the same I've been doing all along through this course. And you can see here these middle nodes are going to be the ones that need to be really considered in the formulation now. And so that's a second order element. So same procedure, use the same approach. Um, And so the first 8 shift functions are the quarter nodes. You can use the same table to recover the first 8 shift functions. The next ones, I'm not giving you the full numbers, the whole table for them. For nodes number 9, which is a midpoint here, 10 midpoint there. These are just midpoints. If you notice here at the bottom edge, and then you have 4 midpoints. At this higher edge and so forth. So these are all midpoints at this point, these shape functions. I'm not providing all these values. You can find them in various books. But the bottom line is that you do have 20 shape functions because you have 20 nodes. And notice how at each node there's three unknowns, the deflections in three different directions. Bottom line is once you have these shape functions, they're the same for every element. Secondly, we're using the mapping, right, to be able to go from the natural coordinate system to the global coordinate system. And we're using the same shape functions that we're using to approximate the solution. That's why it's called isoparametric formulation. And the only thing that contains the geometry information in this formulation is Jacobian. In bold is known, you know, in bold, which has all the shape functions in them. So I know all this. I know the derivatives of the shape function, so that's easy. And I'm going to use this formula here, Jacobian times all this, to figure out what B bold is. And notice how B bold is broken up into blocks to make it easy to calculate. But everything here is fairly straightforward at this point. I'm not going to make you do any three-dimensional problems by hand because that's impractical, but I do want you to learn the process of finite elements in general. The four node first order tetrahedral element is very simple. C3D4 in abaqus, four nodes, and the shape functions are very simple. The abaqus manual, by the way, provides you all 20 shape functions, so that's why I'm not providing it here. You can go to the theory manual and pull it up. You can see here, if I add all these shape functions, you get one, and you can verify for yourself that the partition unity matches, that the Kronecker delta property also works out. But the tetrahedral element is a standard element, and these are the shape functions for it. The 10 node second order tetrahedral element is a C3D10. So there's 10 nodes, second order behavior. Clearly, the first order tetrahedron is computationally less expensive, but has its own problems. I'll discuss that later. Here, you can see that these are the 10 shape functions provided to you, and the nodal locations for the standard element are given here. You can see here for a four node element, the four noded element, the locations of those nodes are given by R, S, and T in this box, in this equation here. And to extend it to the C3D10, you can add an additional number of 6 nodes, and they're located at the midpoints of the edges. So I invite you to draw a tetrahedron and try to plot this point so you can see where it lands. But these are the shape functions for this element. These are the shape functions for this element, while these are the shape functions for the more simpler tetrahedral element. Another point I want to make is not very difficult to figure out what is eta I and zeta I, even if I didn't cover it. I invite you to try it out. All you have to do is figure out what node we're talking about. So if it's node number 9, you should be able to tell me what are the coordinates eta I and zeta I of that node in a cube that goes from -1 to 1 in every single direction. That's how the shape functions were derived in the first place. So it's very easy to figure what that should be and what that should be given that information. Comparison of two different element types. You can see here that the quadratic, the C3D8 and C3D10 get very, very similar results. Get a stretch concentration there. That's fairly close to what you see from books. For if I model the shaft and apply a loading condition, I can determine the stress concentration factor. And the stress concentration factor we find is very similar to the closed form solution of 1.78. It's not perfect, and that's probably because I need greater mesh refinement, but it's fairly close. So this concludes the presentation on how to determine the finite element formulation for 3D. And now I'm going to proceed to the finite element of 2D plane stress and plane strain in the very next lecture. Thank you very much, and I hope you enjoyed this lecture. Have a good day.